ready to go to break, Joe.
Okay,
Yeah.
well, we'll keep the Zoom open and recording. Resume recording. And Dr. Bing Lee, would you like to introduce the next presenter, Alejandro?
Sure. And this is Bing again. I'm more than happy to introduce the students, Alex. Normally we just call him Alex. He's working on the project for the 3D bioprinting, the pancreatic cancer model. This was the collaboration with TRC Institute for Biomedical Innovation. Through the ARCS, I think we established the strategy partnership with TRC Institute. We also signed the MOU between the ARCS and TIBI. Alex, I think it's your turn. Thank you.
Yeah, thank you, Professor Lee, for the introduction. Let me go ahead and share my slide. I apologize for any background noise. I'm currently at lab, so if there's any background noise, please disregard that. Okay, so as Professor Lee mentioned, my name is Alejandro, I go by Alex. This is our project in collaboration with TRC Institute for Biomedical Innovation. The title for our presentation is three-dimensional bioprinting of pancreatic cancer stromal assembloids. Pancreatic cancer is a type of cancer that starts in the pancreas, with pancreatic adenocarcinoma being the most common type of this cancer. In efforts to capture pathopsychological characteristics of human tumors, in vitro models are essential for basic and translational cancer biology. However, current in vitro cancer models lack the native microenvironment where cancer stromal communications and cellular migration take place within the cellular matrix. Our research team promotes an effort in the innovation of bioprinting three-dimensional cancer stromal tumor models for preclinical drug development, personalized drug delivery, and complex biological research such as regenerative medicine. So just to reiterate, we plan to 3D print a cancer stromal assembly. By doing so, we use a 3D bioprinter in which we use a bio ink that encapsulates our tumor and associated fibroblasts. From here, this bio ink is then loaded into cartridges in our bioprinter, and then we go ahead and bioprint these tumor models. So for phase one of our project is to determine our biomaterials ink. We wanted our bio ink to meet 4 certain criteria. The first one was for it to be biocompatible, UV cross-linkable, and possess shared thinning properties. And overall, we wanted our bio ink to be thermally stable. For our biomaterial ink composition, we chose 2 biomaterials, the first one known as GELMA, and the second one known as Laponite. GELMA has been proven to be biocompatible and is UV cross-linkable through a photoinitiator. Here, Laponite possesses shear thinning properties and is thermally stable. So with mixing these 2 hydrogels, we wanted to meet all 4 criteria of our bio ink. So again, we use GELMA and Laponite, which is nanosilicate. We mix these 2 with our cells. From there, we were able to 3D print a scaffold. And then after 3D printing, we UV cross-linked it. So in determining the best concentration for our bio inks, we did a range of 2 sets of concentrations. The first one consisting of 10% GELMA and the other with 5% GELMA. 10% GELMA has been proven to be bioprintable. However, due to its thermal instability, it's very hard and inconsistent when printing. So this is why the incorporation of Laponite will help improve that. And we chose 5% GELMA because it has been proven to be more better for the cells in which they proliferate and are able to migrate within the matrix better. So first of all, we did a print test without any cells to see if we are able to extrude our bio ink. So with 10% GELMA, we saw that we're able to extrude with 1%, 1.5, and 2% Laponite. And when we increased the concentration of Laponite with this concentration of GELMA, it was too viscous to extrude. And that's not what we want, since high pressure can reduce cell viability. And as for 5% JELMA, we know that it's not printable without lapinite, but we wanted to incorporate lapinite to see if we could modify it. We found that with 5% lapinite, anything below 2.5% concentration of lapinite, it was not printable due to its low viscosity. And anything above 2.5% lapinite, we found that it was printable. After determining these range of concentrations, we went on to do a diameter test in which we printed fibers and measured their diameter ratio. In which, if you look at figure D here, we found that 5% JELMA within the ranges of our lapinite concentration, it had a higher diameter ratio, which meant that the resolution of printing compared to our nozzle was not sufficient enough for us. So we then did the same test for our 10% JELMA, and we found that the resolution for these fibers printed was much higher than that of 5% JELMA. So moving on, now that we found out which ranges of our bottle ink was printable, we next want to test it which ranges of bottle ink were biocompatible. So similarly, we tested both ranges of our JELMA concentration with the respective lapinite concentration. So we tested day 1 to day 10, and we found that 10% JELMA alone was biocompatible, but when we introduced lapinite, the cells proliferated more. So if you look at this graph here, we see that when we introduce lapinite into our JELMA, cells proliferated more. However, when we introduce a higher amount than expected of lapinite, we saw a decrease in cell viability. And this could be seen more in our 5% concentration, where the ratio to JELMA, where the ratio to lapinite to JELMA is much higher. Where lapinite here, we have 2.5, 3, and 3.5%, and we see that the cell viability decreased drastically. So here we have some images of our 10% JELMA by itself. Here we have images with 1% lapinite, 1.5% lapinite, and 2% lapinite. We imaged live and dead cells using calcine and ethylium homodimer, in which calcine stained green for live cells and ethylium homodimer stained red for dead cells. Here in day 1 of our 10% concentration, we see that there's not that many cells, but then on day 7, you see more cells grow. However, for 5% JELMA concentration and its respective lapinite concentrations, we see that even on day 1, there wasn't that many cells, and the higher concentration of lapinite decreased cell viability. And we see that when we increase the concentration of lapinite, even there we had less cells than our 10% JELMA. So now that we were able to determine the biocompatibility of JELMA and lapinite, we were able to rule out 5% JELMA with its respective concentration of lapinite. So then we selected 10% JELMA and the concentration of lapinite. We then went on to test cell-to-cell interaction. We did this with Miopaca-2, which are pancreatic cancer cells, and C3H, which are the associated fibroblasts. So here again, we got our BioLink. We encapsulated our tumor cells in the associated fibroblasts. We mixed them. We were able to print our cancer stromal assembloids, and then we imaged for day 3 and day 14. However, when imaging, we did have difficulty seeing the cells inside of our spheroid, but we were only able to image the cells on the surface. So here, there's not really a quantification of how many cells were present, but just more of a visualization of the cells being there. We aim to see the cells inside of our spheroid by doing histology and slicing our samples. So much like the other images, here we have cell-to-cell interaction where we stain our fibroblasts with alpha SMA, which is a smooth muscle actin. And this is a traditional cancer-associated fibroblast biomarker. And then here we have some images with our 10% JELMA and no lapinite, 1% lapinite, 1.5% lapinite, and 2% lapinite. Here we have some images and where Here we could see the cancer-associated fibroblasts aggregate with our tumor cells, and as well as here in 1.5% laponite, we see our cancer-associated fibroblasts aggregate with our tumor cells. So again, these are just some visualizations of our structure. And here you can see the spheroids, how it has a round shape. But again, as I mentioned, we weren't able to see the cells inside of our spheroid, and we're doing histology for that. That's pretty much it for the time allowed. Here we have some other results where we stain our tumor cells for PCK, which is a tumor invasive marker. And then we also did some rheology analysis for our different concentration of our biolinks. And here we did some SEM images for our 10% JELMA concentration of biolinks. And we also measured some other rheological analysis for our biolinks. And that's pretty much it. I would like to acknowledge Professor Lee, Dr. Ho, and Professor Kelber for contributing his cells to us, and our team at Terasaki Institute, and my peers, part of LSAM. And that's pretty much it. Is there any questions?
Yeah, I had a question. You mentioned UV linking. What is that?
Oh yeah, UV cross-linking. Here, I could show an image here. So once we 3D print, or once we bioprint our scaffold, it basically does not hold the shape. So you cannot pick it up as opposed to after cross-linking it. So when, before we bioprint, here you can see the nanosilicates where they are scattered, but then the UV cross-links the JELMA with a photoinitiator called IGRCure, and that cross-links it and makes the bioprinted scaffold solid, as opposed to right after we just finish bioprinting it. So put simply, UV cross-linking makes the freshly bioprinted, not solid scaffold into a more solid scaffold.
Okay, thank you.
Great. Thank you so much, Alex.
Yeah, no problem. Thank you.
Dr. Lee, again, the next team is also your team. If you want to introduce
Sure.
the next group, Abraham and Paula and Ruto.
Sure. Next projects working is the partnership with Autodesk and the GPL. So we have two projects. This is the first one is the digital twins to utilizing the OpenSys, GPL's OpenSys software, and Autodesk Intrepid. So we're trying to design and additively manufacture the multi-physics optical tracker, for the aerospace application. And our team member today we have Abraham, Rita, and Paula, but we have more students. They will introduce in the slides. Rita. Oh, Abraham, you can start.
Or you're muted, Abraham.
You're muted, Abraham.
My bad. So we will be talking about the JPL ARCS optical tracker with OpenSys here. As mentioned before, Dr. Lee is leading this project, and the team is composed by Henry Wong, myself, Paula Lagozzo, and Rita Wu. So the motivation for us to go into this research is because there's currently many industries facing communication challenges between multi-departmental projects. So often these departments within the projects, they either oversee currently established process and they start developing their own process for a set goal, or two departments could develop the same process or different processes for the same goal. So information and time is lost. So the goal for this project is to using digital twins, develop an efficient process to apply on the mechanical aspects of a space system. And such space systems have the mechanical aspects of specifying, designing, manufacturing, integrating, and testing. So we use a case study where the design problem is involving a star tracker. This star tracker must maintain an orientation for it to perform properly. This star tracker is also subjected to thermal loads, which introduce stress and strain. Also, we want to optimize the bracket, and as we optimize it, we want to assure that we don't introduce more stress and strain, so we can maintain that angle aforementioned. So as we work on this optimization, we have some requirements that help us to stay within the bounds of what we need to deliver, and such requirements are shown here. So in the first step of the project, we needed to design or to develop a computer-aided model or a CAD model. And as we were developing this model, we had to take into consideration the volumetric constraint shown in the left, where we have 175 millimeters on the three-axis. And as we were building the part, we had to keep different bodies within the same object. This will be explained right now. The importance of different bodies comes within the optimization of the part, where we use generative design from Fusion 360 from Autodesk. So in the first image, we see the constraints and the loads application. That's why we had to separate the bodies within the component. So the first bodies that can contain either constraints or loads are the green ones. Then the third image shows us the boundaries of the optimization. So the optimization will not go into the red zone. And the fourth image shows the section analysis of the comprehensive setup for this optimization. So once we minimize the mass, we come up with this type of outcomes. This is the best outcome that we've had so far, where we have an organic shape with a symmetrical optimization, which will be explained why symmetry is important. So now I will be passing to Paula for her to explain the thermal loads.
Hello again, everyone. My name is Paula, and I'm the thermal analyst for this project. So one of the problems we encounter within the object in space is the extreme thermal environment that the vacuum of space poses. So this thermal environment involves unfiltered direct sunlight as well as full shade after the object passes into the shadow of the planet it orbits. So we can observe some extreme temperature differences across a very narrow span of time. And these temperature differences can cause the metal to heat and expand as well as to cool and shrink, which results in thermoelastic displacement of the bracket material itself. Now, this thermoelastic displacement is a huge problem since it can affect the direction that the tracker points in. So as the metal expands, the structure begins to bend out of shape, which means that the instrument is no longer pointing in the direction it's supposed to be pointing in, which results in instrumentation inaccuracies. So our goal for this project is to obtain a tracker model that displaces as little as possible or displaces in such a way as to minimize the deviation of the center line of the tracker position, just so we can keep the tracker pointed in the direction that it's supposed to be pointing in. Next slide, please. So my analysis portion utilized the thermal FEA package in Fusion 360, and I've got a little snapshot of the results from one of my tests right here, just as an example. I tested multiple thermal loading conditions with different thermal loads applied in different regions of the bracket just to see how it behaved under this variety of conditions. And then I gathered the results for total displacement as well as displacement in the individual XYZ directions. Then I created tables with displacement data and performed some calculus to determine the angular deviation of the tracker's center line. And this is what I used to determine whether a bracket design was viable or not. Next slide, please. And right here, I've just got a quick example of what these displacement tables look like with a snapshot of the bracket model I was using, as well as the total deviation angle at the very end. Next slide, please. So after running quite a few of these tests on design outcomes that came from generative design, it became apparent to me that we were seeing deviation in all axial directions. And it occurred to me that we might be able to reduce some of that deviation by building design outcomes that are symmetric about the ZY plane. And the reasoning behind this was to create a bracket in which the deviation on each side of the plane would cancel out, which results in a total deviation that only occurred along the ZY plane instead of all 3 axial directions. And this turned out to reduce thermoelastic deviation across the board. So we decided to continue making models that were symmetric about the ZY plane, just so we could restrict deviation to that plane only. And from these symmetry tests, we actually found one model that satisfied all of our loading conditions so far, which I'll show you on the next slide. So this is generative design outcome 5 under the first thermal loading condition, and it was found that the centerline deviation under this thermal loading condition was well within design limits. Next slide, please. And this is the same outcome, but under the second thermal loading condition. And as you can see, the total thermoelastic deviation is still well within design limits, which makes this the first bracket so far to have satisfied both thermal loading conditions. Next slide, please. So now that we have a promising candidate for the final bracket design, I plan on continuing to test this bracket under more dramatic thermal loads just to find what its functional limit is before it stops performing within design limits. And also I plan on continuing to test any new generative design outcomes to see if any of them fall within design parameters. And ultimately, we'll choose the model that deviates the least under these thermal loading conditions. And that's all I have for you. I'm going to pass you on to Rita now, who's going to tell you a little bit more about our code.
Hello, this is Rita Wu, and I am using the OpenCaesar to create an ontology for this project. And the OpenCaesar has including 2 parts. One is the vocabulary, and the other one is the description. And this image is just showing the vocabulary design for our project. We are currently using the different notation to represent different portion of our vocabulary. We are using daemon to represent the relations that connect two entity together. And we are using the square to represent an entity in this vocabulary. And we are using the yellow circle to represent the property. And next slide, please. This is the result from the OpenCaesar, and this is also the ontology. And this is the thermal analyze part, which including 6 concepts, which the concept is actually the entity in this OpenCaesar stuff. And for example, the thermal, this AI6T61 is an entity, what inside the thermal conductivity 6061 is the property of this concept, also this entity. And this arrow that connects the thermal analyze and AI6061 is called the relation that I just connect these 2 together, use this material relation, same as the other parts. Yeah, that's all for the OpenCaesar part. Any question?
Any questions from the group? Okay. Okay. We can move on to the next team. This is one of our newest projects that we've kicked off. Involves multiple co-Is that includes Dr. Ho, myself, Dr. Lee, the professor from business, Professor Goduzzi, and then a group. This is probably one of our bigger projects that we would say is very much convergence and interdisciplinary, or transdisciplinary is the term that we're using here. But this is the WATT project that deals with working with waste management. And I don't know, Bing, if you want to go ahead and explain more on the project, or Newt, if you want to explain more on the project. Or we could just have the students go right into it.
Yeah, maybe just have students to present.
This is probably one of the newer projects we've just kicked off. So, but we thought it would be important to present at this meeting. All right, so I think, Josh, you are sharing screens, yes?
Yes.
Excellent. And then Melissa and team is a big team, so go ahead.
All right. Well, can everybody hear me all right? I think my mic is on. Yes. So yeah, good afternoon, everyone. My name is Joshua Vasquez. And I'd like to go ahead and introduce the rest of my team members, Melissa Pakumian, David Bell, Mitesh Sawant, and Jinhao Zhu. And like Joe had mentioned, we are all a pretty interdisciplinary amalgamation of a team I am the designer who is going to be involved with this team. But first off, I'd like to go ahead and mention Watt's quick mission and vision, and how we are going to be contributing to NASA's overall objectives. So that will be to accomplish zero waste, climate change sustainability, substantially increasing institutional research capacity, developing a STEM workforce, and commercializing research results to address pressing societal needs. And to go ahead and expand on those little topics right here, I'm going to go ahead and pass it on to the rest of my team. Melissa will be the first to address her part of it.
Thank you, Joshua. Hi, my name is Melissa Bagumian. I am a first-year MBA student under the leadership of Professor Prasad, who is going to be overseeing the business and law aspects of Watt. So I will be assisting in the data collection aspects of this. Next slide, please. Oh, no, keep it in the slide. So we're going to be working on a few things. So first will be the worker's view. Looking at how we're going to be approaching this, we're going to be looking at addressing and pressing a societal workforce, the job satisfaction, the perception and effects to working within waste management, the organizational structure, and the ideas of future and work while it's in the work culture. Next slide, please. Now into the data collection aspects, there's two different things that I wanted to mention here. So in terms of the collection, we're going to be looking at the workforce behaviors, the perception of automation, and the work culture. Now, how we're going to be collecting this data is going to be in three different ways. So it'll either be in-depth interview, through surveys, or through focus groups. And it's very important for us to actually collect this data because it's very, very scarce in terms of research out there with waste management as it's actually gearing in towards zero waste and automation. So it's really important for us to actually collect this so that, you know, future businesses to come can actually utilize our information moving forward. Next slide. And then working and looking at the data and what does it do? Looking into the future for the view of contributions, management studies, human computer interactions, the law and regulations, and the future workforce. And as it pertains to the AI automations, the impacts of employment, independent contracting, and the legal and business frameworks. Now that I will be journeying my legal aspects, I'm going to be transferring over to David Bell, who's going to be talking about technologies.
Hello, everybody. My name is David Bell, and I'm a first-year master's student working under Dr. Lee. And I'm pursuing my master's degree in manufacturing systems engineering with a focus on automation, which is relevant to what I'm working on this project. To date, I have been performing research on technology that can be used for organic identification, specifically to the waste management process. The current areas that I've been performing research on have been in laser-induced breakdown spectrography, Raman spectrography, and AI object identification. And we're trying to find ways that we can apply these various technologies to our purpose here on this mission. And I've been working closely with Mitesh, so I'm going to hand it over to him to talk about what he's been researching on this.
Hello, this is Mitesh Samant. I'm a master's student at CSUN, working under Dr. Lee. The main focus I've been doing researching on is different types of sorting technologies. On the right hand side, we can see the white color image is that the method is known as in-flight sorting. And this, the machine identifies the plastic bottles according to the density and its weight, and then it applies pressure and uses pressure to differentiate the different designs such as PET bottle or plastic bottles. And that's how it sorts it. We are going to use object detection to do waste categorization, and by that we will have the record of all the waste items that are coming in the facilities, and then we will be able to keep a record and sort the waste accordingly. Jinhao is working on digital twin. We'll be using digital twin to improve the efficiency of each and every machine, which will help us recycle more and more products in the facility. Yeah, next. This is the video regarding the digital twin.
Sorry about that. There we go. And yeah, so thank you for your time, everybody. And we'll go ahead and be taking some questions now, if you have any.
Oh, this is Nelson. Can you hear me?
Hi. Yes.
Okay. Yeah, I've seen in the news recently that you know, recycling and waste management is under a lot of disruption right now. In the past couple of years, since China was refusing a lot of recyclables they used to take, is that having? Are there like? Are you monitoring like those big trends in? I don't know what to say. Like, I imagine it has a morale impact on the workforce if the recycling materials are not being used as they were intended. Does that? I don't know. I'm not formulating it well, but
Yeah,
you seem very focused on a narrow thing. But I wonder how globally we are looking.
I can speak a little bit to that, Nelson. We've been working with an expert in the waste management field, and that subject has come up quite a bit on how, as you said, how China has been rejecting a lot of our recyclables. And the reason for their rejection has been, we've been providing them with very poor quality recyclables. And so a big part of what we're considering in our effort is to be able to better quantify what's coming through the QC lines in these recycling facilities, and to give a higher component of recyclables to that end user. So if we can track what's going into those different bins, shall we say, and keep out the trash, and keep it, you know, if it's a bin of PET bottles, and make sure that we're only getting a high quality of PET bottles in there, then that's going to go a long way towards making our recyclables a lot more internationally usable to other industries, or I should say consumers that are purchasing them.
I'd
Okay,
like
thanks.
to add.
I'm sorry. I was going to ask specifically about attitudes of the employees working with the automation. Is like, are you measuring those kinds of impacts on their attitudes?
You want to talk a little bit about that, Melissa?
Yes, we will be collecting that data as well as the time goes on.
Okay, thank you.
Any other questions? Okay. Elliot, Axel, Brandon, again, Dr. Lee, you want to introduce this team?
Sure. Yeah, I think this is the last team project. This is the second project that was sponsored by Autodesk, because we established a long-term strategic partnership with Autodesk and also with GPL. So these two projects, the OpenCISA and Intrepid Digital Twin projects, and also this AI-assisted knowledge graph design, was sponsored by Autodesk. They donated $200K for these two projects. So right now we're working on both of them. The one is for knowledge graph design, so we can solve the issues, and then from the system requirement perspective, and then later on this will be a really good input for the OpenCISA as well, because OpenCISA, they focus on the ontology-based system requirements, and then this is one front covering the design. That one covered the whole design process and also manufacturing. Yeah, we have 5 students in this team. we collab with, I think, 4 engineer from Autodesk and 2 expertise from GPL. Thank you. Elliot.
Yes, so I'm Elliot Sadler. I'm the team lead for the AI Knowledge Graph project. I'm an undergraduate currently in mechanical engineering. I just got accepted for my master's in MSc actually today, so that's good news. All right, sorry, I'm excited, sorry. Okay, so the members of my team, unfortunately, most of them couldn't be here, but there's myself, as I said, mechanical engineering major. Brandon BN, which is the driving member of our team, he's a sophomore in mathematics of computation, sorry, at UCLA. We have Max Slade, who's an anthropology student, Bodia Borjan, structural engineer at UCSD, Axel engineering management as graduate student, and then Francis and Andrew are part-time. Francis is engineering management here at CSUN, and Andrew's actually a high school student. So kind of the journey so far. So kind of a brief overview of what we're doing. Our goal is to develop a kind of knowledge-based system able to support the designer during the detail phase of the design process. And it'll be able to learn automatically from previous designs. By representing the design knowledge as a graph and then enabling the automated reasoning, we can build a single scalable knowledge graph from the multi-model data sources, capable of a new class of intelligent tools for designers and engineers. So short term, we're doing human studies, and we're also doing technology-centered questions like how do we represent design knowledge, which is kind of a nebulous thing, you know, what design can we extract from the CAD. Kind of as a background, like knowledge graphs tend to deal with declarative knowledge, which are things that can be answered with, you know, WH questions, the knows and the who's and stuff like that, as opposed to procedural knowledge, which is a bit harder to like represent graphically. But knowing how to do things, subconscious stuff, you know, those engineering policies that you just know from experience. So kind of as a background for what the knowledge graphs do is they're semantic triples. So they have a subject and then a predicate and then an object. So kind of in a loose term, Eiffel Tower is located in Paris could be something that can turn into a graph where we have 2 nodes, Eiffel Tower, Paris, connected with a blade is located in. So it's kind of a loose definition. This can also then be put into a reasoning engine that can find all the different connections that are available from this sort of data interface. So background, this could potentially be used for knowledge systems and design by, you know, having these complex questions like what's suitable material choices for a bracket given design requirements, and then using a kind of knowledge graph system, we can retrieve the components from existing databases and then kind of answer this question. And there's a number of different questions that could immediately be answered with this sort of system, as this graph kind of shows. So just to be clear, we're kind of partnering with Autodesk. So all of the stuff that we're doing right now is using the Autodesk 360 design database. So everything that we've been kind of working with at that point is moving towards this. Initially, we were actually using the Oregon State Design Repository, but since then we've moved to this because it's a much more robust system. You can see here the kind of assembly data that we've been going with. We have all of this data, and we're using the joints, the assembly trees, the contacts, parametric dependencies, and we're running it through what amounts to a system that's going to be able to take these and turn it into data that we can then quantify into a graph and then actually digitize later. So using this, we're kind of defining stuff as globals, nodes, and edges. So the global is kind of the overall value of the graph that we'd be using, whereas the nodes would be the actual entities that are being related. The edges are then the relations between them, and the system level properties, as I said, would be the globals. So we could have a knowledge graph that has to do with the joints as defined by functions, or we could have to have a knowledge graph that can do with, you know, manufacturing processes by materials. So all of these will be nested into themselves, but that's the overall kind of general structure. So in the real world, this kind of relates to how we're going to be able to define this. So initially the OSDR, the Oregon State Design Repository, was what we were basing this on. And that was mostly because it was actually kind of already geared towards using knowledge graphs. But the ways that it did it were with child-parent relations and then input flows using features and functions and outputs. And this at the end wasn't very useful for what we needed, but the overall structure was good. So when we switched over to the Fusion database, that kind of allows us to take the links into the connections between the parts, and then we can actually create joins, contact surfaces, and actually add different nested graphs on top of different things. So initially, when we started to do things, the overall results were not so great because of particular different things. The body's semantic names weren't really working out. We were finding things were a bit too broad. So we decided to introduce some more focused things. So one of the things that we started focusing on was material prediction. And initially, when we fed it all the information and then said do its thing, there was a lot of confusion in the system, as you can see from the graph. When we actually went in and reduced its options and started manually tweaking things, we actually got a pretty good distribution that cleared up a lot of the confusion. So with that in mind, we started to look at how can we further define what we're doing. So we settled on using functions, because initially when you're trying to define materials, it's an iterative process that is hard to just say, here's one thing, make one decision and be done. Generally, material choice defines your geometry, which then can tweak your material choice, which can do your manufacturing method, which can then shape your processing. So everything is so interconnected that the question of what material to use is really difficult. So what we're trying to do is introduce things that are just functional. So instead of just defining things as what they are, we're going in and we're defining things with highly structured functional definitions. So the idea is if we have a part that's used for supporting, then we can actually assign this a support as the top tier, and then go in and actually assign some second tiers or third tiers. And by doing this, we can build an additional neural network graph that'll actually be able to interface with our material choice. And so we've been going through and manually taking out what we didn't think would be good. We actually went in and found that when we eliminated all of the assemblies that didn't have user-defined joints, we pared it down to a really acceptable number. So as of right now, we're working with labeling functionally a set of data that has been handpicked essentially to feed the AI, the kind of data that we want. We're in the process right now of assigning the functional definitions to the different assignments. But as of right now, it's many bodies. It's several thousand. So it's taking a second. So on top of that, we're also doing like user research, as I'm sure the digital twin projects mentioned, because the research between the two of us is actually tied together with user research, which is being done by the member of our team, Max Slade, who's a graduate student in anthropology. The user research goals are trying to kind of gain an understanding of how JPL works organizationally and how things are actually going to be tied in with any major changes that might come from a system such as this. Right now, their methods are to conduct structured interviews with the JPL flight system engineers. As of right now, we're very close to that. That'll be happening hopefully in the next couple of weeks. And that's kind of where we're at with the project. It's a whole lot. Sorry, I had to talk pretty fast. There's a lot of stuff that got cut out. It's a pretty complex project with a lot of moving parts, and that's the most general overview I could come up with. So forgive me if I didn't include anything. So any questions?
There's a lot of moving parts, but they all have names, right?
Oh yeah, and I even know some of them. So I'm kind of handling a lot of the mechanical stuff, as well as leading the particulars. But the computer programming is almost exclusively being done by Brandon Bien and Daniel Grande from Autodesk. So the real particulars of what they're doing there, I'm in the dark. I'm just a mechanical engineer.
But the overall, yeah, I definitely understand the overall stuff. So if we have any questions, please ask.
So I'm trying to link it back to autonomy, and is this, maybe you said this and I missed it, but is this to enable like more automated design or evaluation or okay.
Yeah, the idea is to be able to take engineering experience and discipline that would take a lot of research to figure out and distill it into something that we can quantify, graph, and then spit out as an answer. So you as a designer, you come in and you say, I want to design a drone, and you start putting stuff together. The system will be able to come in and say, hey, by the way, that's too thick, that's too thin, you should use this material. It's essentially trying to give designers the benefit of the experience of everybody who's worked in CAD. So it's a hugely nebulous thing, and that's in the future. As of right now, we're basically trying to get the system to be able to look at an assembly and then correctly judge what material any given part should be.
Thank you, Elliot. Since we have the Danny Gandhi, he's the engineer, working with us closely for these projects. I'm more than happy to introduce Danny, and also he can also introduce a little bit more background and motivation.
Yeah, absolutely.
Project. Nielsen.
Sure. Hey
Danny.
everyone. I'm a senior research engineer at Autodesk Research, and I've been working with the students for the past few months. I'm the main point of contact on the Autodesk side, and from I guess I can say the benefit from our point of view has been that we have some CAD data that we're looking to publish for research purposes, and so it's been extremely valuable to work with this group to see what might be done with this type of data.
Great, thank you.
Thank you, Danny. Thank you, Nielsen.
Yeah, I was wondering if, sorry, I was wondering if you could use an approach like this to maybe capture like the process of piloting an aircraft, and then use those knowledge graphs either to train an automated system, or maybe even to transfer like expert pilot knowledge to someone who's just learning, training up.
Yeah, I mean, theoretically, if when we succeed, yeah, I mean, knowledge is knowledge. If you can quantify it and put it into the system, then definitely take tweaking to work. But yeah, I mean, that's I think well within the sort of thing. That's partly why this is exciting, is it's leading towards active CAD tools and autonomy in manufacturing, by being able to just distill stuff that we didn't really think we'd be able to quantify and then apply digitally. So yeah, absolutely.
Okay.
Yeah, I think that's a pretty good, the suggestion, because that's why, right now this project was, I think, 3 entities collaboration: JPL, Autodesk, and ARCS. Yes. And we also have a team of, I think Mitch helped us recruited almost 20 employees from JPL. They are involved in different phases for the design, manufacturing, and the system, the design. So we will learn this insight from them, and then later on, this outcome of the project will benefit like JPL's, the engineers, scientists, the technologists, right, to design their new like a spacecraft as well. So that's why we use one Cadre robot as the case study, right, to demonstrate the feasibility and also the probability, for these projects. Thank you.
We're also working with NIST as well to define the graphs and the functions. So it should be industry standard.
Okay, thank you so much, team. I'm going to go ahead and introduce Ramin next. Professor Liu could not be here to introduce. You're here? Yeah, so Ramin's been working with Amir Rahmani and Scott Davidoff at JPL and visualizing hierarchical structure of multi-agent robotic systems. So take it away, Ramin.
All right, thank you. I guess I'm going to share screen.
Hey, Elliot, you're still sharing. Can you stop share? There we go.
Oh, I'm so sorry.
No worries.
Okay. You guys can see it, right? Okay. Hello, everyone. My name is Raman Rufa. I'm a last year graduate student, software engineering at CSUN. My research is about visualizing hierarchical structure of multi-agent robotics system using BPM and notation. I want to thank Dr. Liu, my associate professor in CSUN. His research interests is mostly human-machine interacting and human-machine teaming. And also want to thank Dr. Ingam and Dr. Rahmani at GPL, which during a technical gives us a lot of suggestion and guideline. And also Dr. Davidov, Dr. Lila Crox, and Dr. Kim and Grace Lim and Dr. Rossi, which help us from the beginning of this research. So I'm going to go over till a summary, abstraction of what we're doing. The goal of this research is basically to design and develop the UI software to visualize the hierarchical state machine-based multi-agent autonomy using BPM and notation that can advance the methodology of representing concurrency in a multi-agent system that use behavioral-based systems such as multi-robot autonomy in this case. Multi-robots system or multi-agent system, or in this case, multi-robot system, is basically infrastructure that is an intelligent cyber physical system where robots understand the need of human, and and therefore it's going to cooperate together to fulfill its need. Modeling multi-robot system is a very important aspect of designing proper system architecture, because this model can be used to simulate and measure the performance of proposed architecture. But the problem is that multi-robot system modeling is a very difficult problem, as it contains many dependent behavior that dynamically change due to the current state of the system. Complex behavior for cooperative multi-agent application basically pose a challenge task in highly dynamic environment, as they are encountered in many real-world applications. So I'm gonna go to next slide, and I'm gonna just give you a brief introduction. What is hierarchical state machine in the beginning? So hierarchical state machine is basically a finite state machine that whose state themselves can be other state machine. It basically is a finite state machine within finite state machine. Hierarchy is a useful construct in many modeling formalism and tools for software design and requirement and testing. Some of the advantages include maintainability, which means adding and removing a state. It's not when you add a removed state, it's not necessary to change the condition of all other states that have a transition to new or old one. And big changes are not susceptible to the error that may pass unnoticed. And the second advantage is scalability. Finite state machines with many states lose the advantage of graphical readability. Basically becomes a nightmare of a lot of boxes and arrows, which you cannot really read it. And also it's reusable, as the conditions are inside the states. The coupling between the states is strong, and being practically impossible to use the same behavior on multi-projects. And then I'm going to the next slide. I'm going to talk about what is multi-agent robotic system. So multi-agent system basically consists of the agents and their environment. Typically, multi-agent system research refers to software agent. However, in this case, agents in multi-agent systems could equally well be robots, human, or robot-human team. a multi-agent system may contain a combined human agent teams. Some of the characteristics of this multi-agent system are autonomy, which means each agent at least partially or independent, self-aware and autonomous. Basically, they think for themselves. They have a local view, so no agent has a full global view or system is too complex for the agent to exploit such a knowledge. So therefore, each agent has their own view of the overall environment. And also the last one is decentralization, which no agent is designed to controlling the whole system. And so the notation that we're going to use in order to represent this complex system is a BPMN. So what is BPMN? Basically, BPMN is the object management group specification. The primary goal of a BPMN is provide a graphical notation that is understandable by all business users, from business analytics who create the initial draft of the process to technical developer who's responsible for technology that will perform those processes, and finally to business people who will monitor those processes. But in this case, basically, the feature that we want to add to our BPMN model, it's a BPMN sub-process in behavioral control. So sub-process is a compounding activity that represents a work that can be broken down to the final level of process model detail. Additionally, sub-process can be represented in expanded or collapsed view, as you can see in the picture. You can see the expanded version. Collapsed view indicate that sub-process can be opened up to show the lower level of process. I'm just going to go over some of the example of different kind of sub-process that we have. So we have a loop marker, we have a multiple instant marker, we have an ad hoc marker, and a compensation marker, which each one has a different usage. A loop marker defines a repeating sub-process, which means the sub-process will start again after it reaches to the end. A multi-instance marker attached to the sub-process represents several instances of the same sub-process. An ad hoc sub-process indicate with the which indicate with the tilt symbol. This type of sub-process contain a number of the embedded inner activity, which are intended to be executed flexibly. And so this is just a quick introduction about how we use the BPMN to represent our sub-process. And at the end, just want to say how this research will basically help us to basically develop the method, an algorithm for visualizing HSM-based complex multi-agent behavior during execution debugging. So visualization tool for HSM or hierarchical state machine using BPMN can basically aid the system engineer and operator to build and monitor our hierarchical state machine. And at the end, it will reduce the complexity of behavior construction that ultimately improve the scalability of hierarchical-based system, and which can be a great help for operator to basically control our multi-agent system. And that's it for me. And if you have any question, I can answer. Thank you.
Good question, Ginu. I will make sure to collect all of the team slides and put them up in a maybe a box or something to download. Also, there's about 3 or 4 teams that recorded their presentations that couldn't be here today. I'll be able to provide that as well in a link.
That would be super helpful. Yeah, I had a question. So multi-agent robotic teams, one of the critical components to that is communication. I'm wondering if your visualization tool has a way of representing communication between the different elements, and then things like what the uncertainty level is with that communication, or error rates, or things like that. Like how much do you trust that communication path? Does that make sense?
Well, I think that would go through our like a ROS, like a robotic operating system. The thing is, we just want to. I know they already use BPMN for visualizing that communication. The only thing that because they're autonomous and they might be in a different state, which can be complicated at some point. We just want to add the feature that it actually shows the sub process in a way that it's easier for operator to basically vision that. Yeah.
Okay, thanks.
Yeah.
Any other questions? Okay, so we've entered our 2 o'clock hour now. I appreciate everyone being here, and I appreciate the NASA, the review committee as well, for your time today. Thomas is here. So Thomas, do you want to introduce the next team?
Yes, excited to. Hi, everybody. I'm Dr. Thomas Chan. I'm an assistant professor of psychology, wearing my ARCS shirt. I love it. It fits great and so soft. Thank you. I'm going to be introducing Jeremy, Allison, and Jaslyn, who are going to be presenting our work with trust and autonomy on Mars missions. And I'll hand it over to them because they did a lot of the work, and their eyes are hurting because they're such great researchers. Okay. And hi, everybody.
Hello, everyone. Okay. Hello, everyone. My name is Jeremy. And today, Jeremy, I and Jaslyn will be presenting this presentation. This is Jaslyn. And we did our study on how trust and intention could possibly play a role in in autonomy for future Mars missions. And I just want to say it was really cool to even be able to. Oh, okay, there. I was making sure it would work. It was so cool to be able to work on a project that involved the Mars mission, because there's so much coordination just to get the rover to Mars. And once you get the rover onto Mars, it's a whole different story, because now you have to worry about all these mission deadlines that people want to achieve, but there's only so much time and resources that you can get from the rover itself, and even the time you have on Mars. So we want to we saw that in doing this project, we saw that planning and negotiation played a huge role in how they were able to meet those mission deadlines. So now it was the idea of okay, so we know that planning and negotiation are one of the key things to getting missions done. We want to focus on how we could use maybe autonomy to add into the mix of planning and negotiation. So there was 2 things that we really wanted to focus on with planning and negotiation for future autonomous missions. One of them was seeing how intent was specified and communicated through the JPL personnel. We saw that there was different ways in how they communicated with each other, and we wanted to see if maybe autonomy could identify the intent and maybe possibly use it in future missions. Another thing we want to look at is the roles that each JPL personnel played, and seeing if autonomy could maybe add to those roles, or even use those roles to help with the planning and negotiation process. Let me go on to the next scene. So we realized that planning and negotiation was there was a lot of layers to it, and one of the layers we found is that there was 2 different perspectives within the JPL operations personnel. One of them was the science perspective, and the other one was engineering perspective. And we realized that these are 2 groups that communicate differently. So one example of that would be this quote from one of our participants. We struggle with the science to engineering communication. On the science side, we're too wishy-washy, or we're not willing to give a firm limit on what we're asking, or we give too much detail, irrelevant detail from an engineering perspective. So in seeing this, that we had this layer and there was multiple layers. We created a study that had 10 interviews that each lasted about an hour, which we had about like 10 hours of interviews in total. The participants were Mars surface mission personnel, and majority of them were from JPL with one external. Most of them were on the previous Mars mission and the newest Mars mission. A lot of them were veterans, with a few brand new to the Mars missions in general. And each one had various roles coming into the Mars missions. So you had like science operations coordinators, science engineering liaisons, and so forth and so forth. And how we went about with this study, we used atomic research approach. We started with grounded theory, which is facts, and then from those facts, we created insights. And with those insights, we use those insights to test the protocol and adjust it to see if we can really solidify the facts that we had found earlier. So we did iterations of this to make sure that our end product, being the nuggets, was solidified, and we can be really sure about the nuggets coming forth. And again, we spent a lot of hours of just staring at the screen and going through iterations over and over and over again. That's how we went through breaking apart all these layers. And now Jasmine will explain the results of our work.
Hi, everyone. So thank you, Jeremy. So getting into our results, we have 3 latent themes that we found of corporate knowledge gluer, bridge builder, and efficiency optimizer, with a total of 14 functions. And so the operationalization for corporate knowledge gluer is that these people fill in any mission relevant knowledge gaps to update rotating or missing personnel. And for bridge builder, they act as conduits to foster collective understanding between science and engineering teams. And for efficiency optimizer, these people streamline the task and attention of teams to meet mission deadlines. And so just getting a little more into the specifics of each latent. For corporate knowledge gluer, we have the 4 identified functions of information clarifier, cocktail host, breaking news reporter, and urgency. Sorry, hold on. An urgency umpire. And so for cocktail hosts, these people act as a day-to-day point of contact to maintain mission structure. And so we have an example from one of our participants. We have a quote that says, "That person who's listening to every conversation efficiently to make sure that the right people are hearing the right information and understand the constraints and the intent of why we're doing things." And so this is our evidence to support our identified function of cocktail host. And so we just want to highlight that science decisions evolve with intense verbal and nonverbal communication among operators within this latent. And so for the bridge builder latent, we have our identified functions of intent translator, room reader, people reader, room phantom, day trader, and opinion validator. And so intent translator communicates and improves comprehension of planned goals between scientists and engineers. For example, we struggle with the science to engineering communication. I put a lot of thought into how to translate the science into intent, and then ask the engineers and ask that the engineers understand. And so within this, we want to highlight within this latent that these soft skills that operators demonstrate suggest that autonomous systems will strongly benefit from humanizing, as this bridge builder role specifically has a lot of humanizing elements to it. And so for efficiency optimizer, we have constraint highlighter, forestry juggler, urgency umpire, and options funneler. And so for options funneler, these are the people that narrow down decisions for science and engineering teams to pick from. And so you are a facilitator, you are not the decision maker, you provide people with a set of choices. And we wanted to highlight that operators express preferences, significance, and implications of choices available to optimize planning, which can inform communications interfaces of autonomous agents. And so going into our discussion, we have a paper that we recently released specifically on this study. And if you would like to see this paper, we can send it to you. And so one of our main points into that we want to highlight for this study is that negotiation and planning is very complex, and it requires intense communication and coordination among the operating teams. And specifically going into the constraints, option space, and implications for planning choices. And it's important to demonstrate soft skills that ease communication and coordination as detailed earlier. And so with knowing this, our future research will be related to focusing on the intent that operators will need to consider, multiple scenarios where resources and other conditions can vary, and further research to see how we can develop these user-friendly ground software tools to aid planners to figure out gaps within ambiguities in their intent expression, and to understand implication of their planning choices, since negotiating and planning is very complex. And with that, I would like to thank all of you for attending this presentation, and our collaborators at JPL, ARCS, NASA, and funding from the NIH.
So, was your intent to replace some of those human functions with autonomy, or to find ways that autonomy could help the humans do those functions more effectively?
Yeah, sorry.
Or maybe both. I don't.
Yeah, that's a great question. So I think that sort of leads into our future directions, because we would want to ideally see if there's a way to have both. A way to have these the software that they use to sort of have these machine enabled algorithms within them to see if they can make this process any easier, but also to have tools to support the planning and negotiation in general, because we noticed that there is a lot of soft skills that are needed within this whole process. So yeah, that's something that we're looking forward to further investigating.
Okay. Yeah, some of those roles seem like they might be well suited to autonomy, and then other ones not. Like people reader might be a really hard thing to teach a machine how to do, right?
Yeah, exactly. And we agree with that. But yeah, I think it'd also be very beneficial if we can also, because this was all done online, like we had these interviews over Zoom, so it would also be really helpful if in the future we could see how they work in person and possibly build off of that as well. Oh, machine people reader. Black Mirror. Yeah.
Okay.
Thank you
for your question.
Yeah, thank you.
Thank you. Thank you, Thomas. Thank you, team. Dr. Hartman, Emil Hartman here. Do you want to go ahead and introduce Jessica?
Yes, hello. So the next presentation here that we have is for the Compact Autonomous Exploratory Search and Rescue Rover CSER project, and this is based off of the JPL Puffer concept. And today we have Jessica Frederick, who is one of our undergraduate research fellows, who will talk about the research.
Hey, Jessica, you're muted.
Hi, everyone. I'm Jessica Frederick. I'm a senior in mechanical engineering here at CSUN, serving as the ARCS fellow and team captain for our systems engineering research lab. Professor Herman, okay. Our research lab is a collaboration between ARCS as well as we have a student from Channel Islands incorporating 3 platforms: our mobile ground control station, our campus autonomous robot tours, as well as the Caesar rover. So for robotics and search and rescue, utilizing robots in search and rescue offers many advantages over purely human-based efforts. By deploying a single robot capable of remote controlled exploration, there's an immediate reduction in the risk of harm to human personnel. These robots are capable of exploring regions that humans simply cannot, whether that's small spaces resulting from structural collapses or natural caverns. The mapping capabilities of search and rescue robots can also contribute significantly to understanding the condition of an operation area, so that search and rescue and engineering personnel can make better informed decisions regarding the safety of a structure and how to evacuate an area. By adding autonomous capabilities to a robot, the needs for independent human operation is reduced, freeing more human resources to be used elsewhere in our operations. Deploying a collaborative team of robots can aid in developing a complete survey of an operation area efficiently and without risk to human life. Increasing the efficiency of search and rescue operations in this way ultimately serves to save time as well, which can improve the odds of survivability for victims, whether they're lost or trapped in these environments. So search and rescue robots for NASA space missions. In the same way that robots are of great importance in search and rescue efforts, they're also extremely important for space exploration. Whether the robot is exploring rugged terrain on behalf of a first responder here on Earth, or whether the robot is exploring caves for astronauts on another planet for scientific research, both of these are useful tools enabling access to locations that humans cannot normally access. So our current project is inspired by JPL's Puffer rovers. The version in the first panel is intended to be a foldable pop-up rover with flexible circuit boards to be compact for space travel. The second design we see here, it incorporates off-the-shelf electronics to be cost-effective, as well as to develop autonomy capabilities. And then here we have the Cadre rover. It's still in development and is being considered for Artemis space mission. Exploration of these puffer designs is being used to develop a small low-cost rover used for exploration in multi-robot teams in high-risk environments. So our particular platform, the Caesar rover, to help illustrate the practical goal of this project, the current Caesar team has developed a storyboard demonstrating an expected use case scenario. An emergency occurs, posing immediate risk in an urban area. This could be fire, an earthquake, or a flood. There have been severe damage to a structure that is potentially endangering the lives of individuals trapped inside. But here, the Caesar rover enters into a building operated via remote control or with autonomous assistance. The robot will be able to navigate through sections of the structure that may have collapsed, making them completely inaccessible to human rescuers. The robot is able to transmit live video feed, depth data providing a 3D map of the interior of the damaged structure, and data on environmental hazards present, such as gas leaks, all while searching for trapped human victims. This data shows that, or this data allows the human team to make well-informed decisions regarding safety points, evacuation routes, prioritizing structure entry, and necessary equipment to perform a well-coordinated rescue operation with the highest probability of success. So exploring the mechatronic systems. So these are previous CSER designs. We have design A1 and A2 that are previously designed specifically by the senior design team. They explore fully 3D printed chassis and deformable wheels. And we have design B, which was developed based on directly off the A puffer as a mobility platform used in testing software. And here we have an exploded view of the A2 design featuring its internal components and sensors. So our design process has been guided by the intent on meeting specific requirements for the robot, as well as improving the work already done by previous teams. The first design requirement we want to address is impact resistance. So we want our vehicle to withstand a drop from roughly 10 feet. So our proposed design utilizes a dual aluminum frame plates connected by standoffs. This was inspired by drone chassis designs. This metal substructure will provide structural support to the 3D printed chassis, and the intent is to improve upon the previously fully 3D printed design. Our next design requirement is to address ingress protection. The rover will have resistance to dust, water, and heat. Our design proposal to address this requirement is to manufacture 2 3D printed external shell pieces and press fit them together. The previous design had many separate pieces with no sealant, and so the purpose of reducing the number of external pieces and having this press seal fit will be to increase protection for the electronics. As the rover navigates through rugged terrain, it needs the ability to operate after landing from a fall in multiple orientations. To address this, our design proposal implements a symmetric chassis with a straight back tail. 2 dual cameras will be used so that it may operate whether it falls facing forward or downwards, and increasing the field of view. The previous chassis designs did not consider reorientation. The wheel design is another opportunity for exploring the design space and addressing design requirements. To continue to reduce impact forces to the motor and chassis from a fall, and the current design proposal is to continue with an airless tire. However, it is to incorporate 3D printed spokes in addition to a deformable hub. This previous design, in the previous design, airless tires were roughly a pound each. So incorporating 3D printed spokes will ideally reduce the overall weight of the system. These are a few of the sensors and electronics that are being explored through our iterative trade study process and to aid in the continuation of our preliminary design. Currently, our ongoing work is to complete review and manufacturing of our new design, sensor integration, software integration, testing the mobility platform, and outreach to search and rescue personnel to improve our design requirements. Thank you.
Thank you. Any questions for Jessica?
I have a question about the very last item on your last slide, the outreach to, I don't know if you've had a chance to do any of that, but I was curious what you were hearing from them in terms of requirements or how they think they might be able to use devices like this.
I have not had an opportunity to set up an interview yet, but the plan is in process. I have been in contact with a person specifically in LAPD. So I just need to conduct that interview, hopefully soon.
Okay. Yeah, we've had some conversations, we being NASA, with like firefighters about, you know, how we might be able to use different or develop technologies that would be useful to them. And, you know, often the answer is, even if we developed a technology, they wouldn't have the money to buy any of them and use them. So I'm kind of curious if that's common among other groups beyond like forest firefighters. But okay, thanks.
I'll definitely take it into consideration when I ask them.
Anyone else?
Oh, Curtis, I can answer that briefly, Curtis. So course, there's a number of different routes, and one that, I think involves really regulatory changes, right? If this is part of the regulation that requires, our fire department to use robots and more, like even carry GPS, right? In the past, we worked with fire departments, they don't have GPS even. So I think one route that we've been discussing and talking, thinking about ways is if there's regulation required that they wear it, have it, and then that would naturally get them the funding from the taxpayers, from whoever that benefits from the services to pay for it. But that's just one aspect of it.
Yeah, that makes sense. Thanks.
Okay, thank you. All right, Dr. Chan, you're back up.
Oh, hello again. This has been amazing. You guys are blowing my mind. So I love all the stuff that's going on here. So next are my other two actually ARCS fellows, Maria Pena and Jared Carrillo. They're going to talk about their work with EVA, autonomous flight simulator system, and also with a NASA Suits, which is developing augmented reality for the next generation of spacesuits, those capabilities. So Maria, Jared.
Hi. Hello, everyone. Let me go ahead and share this. Okay. Sorry. Okay, awesome. So this is titled, hi, my name is Maria Pena. Sorry. This is titled Resilient Autonomy in Trust Machine Interactions, TMI. This was with 510 Systems Engineering Integration at Armstrong with collaboration with my mentor, Nelson Brown. So what is the problem? Why are we doing this? So success in technology is very dependent on, the level of trust that we have in these systems. So we can have these systems to help us, these AI machines, but if we don't trust them, I wouldn't say they're useless, but they're not as usable, I guess you can say. So that's what we were looking at here, and the project overview. So Resilient Autonomy team tests the maturity of technology and inform airworthiness requirements. So finding a path to certification for autonomous aircraft. And my role was to observe and provide previously unknown insights that could improve the bidirectional relationship in human-computer interactions with EVA. So my objective was to obtain a holistic view of work previously done with EVA and look for recurring themes to generate hypotheses that can then be studied in a controlled environment here in the CSUN EVA lab. So how did I do this? I went about this in an ethnographic study. So what an ethnographic study is, the study of the culture and social organization of a particular group or community. And it's both the data gathering and the development of analysis of specific peoples, settings, or ways of life. And the way I did this was I analyzed mission reports, I reviewed simulation videos, and I did interviews to get that holistic view. So the framework by which I looked at everything was through this trusting technology. So this initial trust formation, which can be compared to, for example, how people say, make a good first impression because that's the one that stays with people. So making that first contact with the technology is very crucial because it sets the tone for further interactions with it. So it helps develop this continuous trust in that technology. And so this trusting technology has three branches: human characteristics, so the person's ability and personality; the environment characteristics, so the culture, the tasks, and the institutional factors; and technology characteristics, performance, process, and purpose. So this third category here, the technology characteristics, has three trust dimensions. So performance, which is the usability, reliability, collaboration, and communication; process, which is the transparency and explainability; and purpose, its goal congruence. So the way, before I explain how I went about looking at everything from the data collection, the way I did the data collection was I looked at the mission the project mission log and tracking, which is a master Excel sheet that contains all the simulations ran. And within this, they noted any anomalies within the simulations. So I targeted those specific simulations that had anomalies reported, and I went and I looked at the mission reports. And from the mission reports, I then went and looked at the simulation videos to sort of set the scene and hear the conversation that was going on as these anomalies were being presented. And I conducted interviews as well. And from this, recurring themes occurred. So the first one is communication, connection problems, the internet bandwidth, people's screens were being frozen, but as also team collaboration. So a quote from an interview was that, the first sims weren't necessarily about looking at EVA, rather they were looking and starting to build a means of communication amongst the two groups being the users group and the coding group. So facilitating this communication. The second reoccurring theme that happened was performance. So confusion towards an atypical maneuver. So why did it maneuver this way? Why did it turn left instead of right? I was expecting it to go straight. So not necessarily doubting it, but more trying to understand why it was doing these specific maneuvers as opposed to the expected ones. And the third one was competence. So a lot of not only hearing the feedback, but incorporating the feedback definitely helped to, improve the system and help that facilitation. So no one individual was responsible for the whole thing. It was this back to this collaboration. And some general notes made from the data collection, was trustworthiness in autonomous systems exceeding human performance. So a quote that really stood out to me in an interview was human error versus computer doing real math, which one comes up with the better answer? And the safety assurance system. So its ability to rapidly jump from one move to the next without hesitation and having this situational awareness. So one person mentioned in an interview, as they were watching it, they didn't have much of the situational awareness to really understand what was going on. And EVA was picking a better way. So this goes back to the performance of not necessarily doubting the machine, but rather trying to see, understand why it did a specific maneuver. So in hindsight, looking back, they were able to see that EVA picked a better way because it had this situational awareness, which therefore exceeded the human performance of it. And some future work here is within CSIN EVA Lab, my master's thesis in machine interactions, which I'm knee deep in right now. Some acknowledgements: my mentor, Nelson Brown, my academic mentor, Dr. Thomas Chan, the Resilient Autonomy team, Lisa, who is the coordinator there at Armstrong, and ARCS as well. And this is just a little highlight. I was on the cover of the internship booklet, which I was really proud of. So that's just a little side note there. And yeah, thank you. Jared?
Yes, hello. I'm going to share my screen. Okay, can you guys see the screen? All right, cool.
Yes.
All right. May not go well. I bet. Okay. Hello, my name is Jared Carrillo, and today I'll be presenting on the work I have done for ARCS this past semester. The title of my work is Assistive Augmented Reality Recognition, Incorporating Machine Learning in Daily Operations. Some of the initial work I did for ARCS were related to other projects at the time. This includes stuff from Massachusetts competition and EVA project, which Sharkus is in charge of. In these projects, my work consisted of some UI elements such as the dashboard for the autonomous drone in EVA and the AR heads-up display designed for astronauts in NASA suits. In both cases, my work relied heavily on creating proper interfaces for operators to use. These interfaces were made to make things easier for them or to enhance their capabilities in a sense. Following this train of thought, I began my project with Dr. Chan, and as he is a professor of gerontology, the project I began working on was closely related to his field. The premise of this project was to create an AR application using Microsoft's HoloLens to aid people with memory impairments, specifically in this case, helping people remember their close friends and or family. The program would use facial recognition to detect an individual and bring up content such as their name, age, plans, or just overall description of them. It would also pull images from one's camera roll of them and reconstruct the photo in a sense. These images were treated as their memories, and if the artificial intelligence detected snow in the photos, then it would generate AR snow at the person's feet in hopes of potentially kickstarting a memory. The HoloLens is too weak to do this machine learning on its own, so Jetson Nano was used to do the heavy processing. Case was designed and 3D printed, and the battery was added for portability. In this slide, a basic sample is shown. This is essentially how the program works. It is not fully finished, as currently there is no connection to a phone to pull images automatically from, but the core tech part of it's finished and it's running. Here's another example with a different person, as can be seen there, are different scenery types depending on what memory is pulled up. The program is utilizing Microsoft's MRTK Unity platform to do all the augmented reality components. And as for the machine learning components, the darknet neural network and YOLO v4 model was used to train the weights necessary to handle all the detection in the scene in real time. Oops. The current iteration of this project is tailored heavily to helping those with memory impairments, but it can just as easily be converted for other uses. During the NASA suits competition, it was clear to see that there can be a lot of tools developed to help astronauts up in space. For example, when it comes to finding items in space, object recognition would speed things up for sure, be it either to find tools on a ship quicker or find new locations of interest on planetary surfaces. Even without any onboard artificial intelligence, the AR interface itself is a great way for data information to be presented easily and efficiently to an operator. Some future directions would be to take what I have done here and incorporate it back into NASA suits competition once again. Another direction would be the 37th annual CSUN Assistive Technology Conference. In this conference, we submitted a version of this project that has been developed more and can aid people more. Some examples include creating daily tasks for people and generating augmented paths for them to follow for the day. The idea was to create an AI augmented caretaker assistant. And of course, as this program is focused on NASA, a major future direction would be to incorporate this technology to help astronauts, such as developing object detection software for locating items or new locations of interest. And to finish my presentation, I just wanted to thank all the people in my lab who helped me on this project. The machine learning part took a lot of data to train, and so I'm glad I had others to help me with that. And I also want to thank NASA and the Department of Defense for the support on this project. And that's basically it. Thank you for listening.
Excellent.
Thanks. Forget the astronauts. I need this when we go back to the office.
What's your name again? Right? Again, you could have somebody, the tip of the tongue, you get people's names. Imagine this in a social setting or a dating setting.
Yeah, well, I'm worried that con artists would use it to, glean information off of Facebook or whatever, and then pretend to be an old friend of mine and, get my confidence when they shouldn't have it.
Sometimes every time Thomas started talking, I start hearing like dating and then proposal and then marriage and then children. So all this.
I know. I'm trying to bring the human part. I'm too human.
Well, any other questions for Maria or Jared? Okay, we have one more presentation for today. Newt.
Is Kevin Zemlik on, Joe? He's also a co-supervisor with me, and I don't see him.
For this final project? No.
Yeah, so I'd love to introduce the Mother 3 team. They're going to explain to you what Mother 3 stands for. Yeah, but this is a project in collaboration with NASA, funded by the Air Force Office of Scientific Research. The interest from the Air Force on building, extending some of the theoretical trust model, and that's what requires us to study a group of systems that have high level of autonomy. And with that, I would turn it over to Jessica, Karen, Andy, Sean, and I don't know who else is on the team. If I forget somebody, I can't see all of you. But okay, so Jessica and the team, take it away, please.
Thank you. Can I get the screen sharing ability?
You should have it now.
I got it. Thank you. Great. Can everyone see? So hello, everyone. This is our overview presentation on our 5-year project to model trust in heterogeneous R3 human-machine teams. Dr. Ho already introduced us all. I'd like to also add that we are joined by Cesar Flores, a psych student who is joining us as an associate, and folks who were not able to attend today include Liz Knight from anthropology and Josue Gomez from anthropology. So our study seeks to address a gap in current research studying trust evolution and calibration in heterogeneous R3 human-machine teams. This context for heterogeneous R3 defines contexts involving real users, real systems, and real consequences. So these are contexts in which multiple real, highly autonomous machine teammates and real human teammates operate together. Heterogeneity is often characterized with varying degrees of team member collocation, collaboration duration, vehicle types, and capabilities. So in a sense, our project is twofold. In order to study trust in HMT, we must also define the scope of heterogeneity in these contexts.
So to address the gap in the literature regarding trust evolution and calibration, we're conducting a 5-year study to do the following. We hope to obtain foundational lessons and insights on how trust is calibrated and evolves from the time the heterogeneous R3 HMT is deployed until the level of trust reaches a steady value, if any at all. We also want to identify how technology and non-technology related factors such as organizational, cultural, and personal factors can influence the trust evolution. We hope to validate extant theoretical trust models using the Lee and C 2004 model as our baseline against trust calibration and evolution of heterogeneous R3 HMTs, adapting and extending it when necessary. We also hope to generate hypotheses for trust evolution and calibration in heterogeneous R3 HMT contexts, and formulate research questions and identify pathways to translate the results of our project to applied research. This project has direct contributions to NASA by identifying a model for heterogeneous trust in NASA systems. Our study on NASA systems is funded by the AFOSI.
As the context for our field study, we will use 3 contemporary heterogeneous R3 HMTs of NASA systems to which our research team has access to. Our first R3 HMT is the JPL Mars 2020 HMT. The Mars helicopter was mounted the underside of the Perseverance rover on the journey to Mars in July 2020 and became operational approximately 9 months afterward. Our next R3 HMT is JPL's team CoStar Sub-T HMT, which consists of a team of robots of varying ground and aerial capabilities, a ground control station human operator, data analysts, engineers, and human mission operators and planners. This team participated in the DARPA Sub-T Challenge last September. Our R3 HMT, third or last, is NASA Armstrong's Resilient Autonomy Project, HMT, and the Traveler mission. Sponsored by the DoD, the Traveler's concept of operation involves the human mission controller specifying high-level mission direction and execution information that allow the drones to autonomously launch, transit, interface with the personnel on the ground, use its onboard agents such as the moral compass to make moral decisions, and execute recovery from contingencies such as emergency landing, and generate post-flight information for data analysts and mission controllers to assess the mission effectiveness. Because we are a 5-year project, we are continuously looking for new R3 HMT that we can study.
So our research on trust and HMTs within the social sciences is often relegated to psychological human factors study, which rely heavily on quantitative methodologies. Based on the strength and success of previous anthropological HMT research on AutoGCAS, we have proposed some unique applications of ethnographic research to the study of R3 HMTs. Our field study will be designed in the form of these 3 case studies, one for each heterogeneous R3 HMT that we have described here. Our methodology employs a set of complementary methods, including case study, extended case study, and an approach known as iterative rapid assessment procedures. We will be collecting data over the next 4 years using surveys, semi-structured interviews, and participant observation. Our data will be interpreted on an interrelated case study design based on job roles.
Anthropological research is about understanding cultural frameworks and context. Since the beginning of this year, we have been conducting what we call non-invasive planning operations. These are informal actions, informal in that they're not considered to be data collection methods that will show up in our final report ratings, but still help us understand the complex sites of interest as they will be situated in our 5-year research project. Our sites of interest are complex, fast-paced, and generally inaccessible to the public. Therefore, it is essential to begin building rapport early. As the slide demonstrates, we have begun this report building in the following ways. With the CoStar sub-T of HMT, we have gained access to their weekly meetings in which over 60+ members come together to debrief their progress on the DERPA sub-G challenge competition. And we as fellows observe human-to-human teaming interactions as they go over their meeting. We also have biweekly meetings with the Resilient Autonomy Project Senior Chief Engineer, which provide us very heavy guidance on HMT-specific questions and survey and semi-structured interviews that we hope to conduct with their members in next year. And they have also helped us organize discussions between the Resilient Autonomy team members and our team, which led to this very insightful presentation in the Resilient Autonomy team, in which we received positive feedback from the SA team members with over 20+ attendees and how they view trust and autonomy. And also, we also talk with the collaborators or the stakeholders in our sites of interest and establish rapport with them and informally discuss and define the concept of heterogeneity in HMT context. And we are slowly gathering more information about human and non-human agents involved in each HMT.
All right, so based upon the efforts described and hours of informal conversations with team members, we identified the following nuances in ways that each team thinks about the term heterogeneity in the context of their own R3 HMT. The Mars 2020 mission team appears to emphasize resource allocation and promotes the idea that each agent has different capabilities and dynamics, allowing the autonomy to be seen as an extension of the human team member. This line of thinking from the Mars 2020 project points to increased concerns for the non-human members, especially taking into consideration the interplanetary time differences and the incredible financial risk that's involved. On the other hand, the JPL CoStar team defines heterogeneity with a focus on human social interaction. Different robots, teams, and agents all work together to achieve a common goal, with their thinking about heterogeneity placing great importance on the bonds between human team members. Social interaction at meetings is emphasized, as are informal get-togethers at the homes of the senior members. The increased reliance on human-to-human social cohesion may be related to the nature of the past competition in September, in which only 5 of the 60+ team members guided the robots through the challenge. Each member had a specific role that relies heavily on the other 4 to achieve mission success. And finally, the Resilient Autonomy team emphasized fluidity with regard to role allocation in their discussions of heterogeneity. Different roles are assigned and picked up pragmatically due to varying conditions of flight risk in the EVA and Auto GCAS software. Our subject matter expert suggests that heterogeneous teaming needs to be flexible, complementary, and ideally seamlessly performed. While obviously not conclusive, this informal work counts towards coming up with a generalized definition of heterogeneity in R3 HMT context, which has given us a chance to establish rapport, gain access to future research sites, and becoming grounded in the work being done by our future participants.
Now, we know a lot of you are probably interested in the progress and the next steps. So due to the pandemic restrictions, there have been a lot of complications with the IRB process. And that's made, studying the current case a lot more difficult. But as such, we've devoted a lot of our time into refining the IRB application and conducting a more thorough literature review. Among that, we're also doing a lot more like preparatory groundwork, such as building rapport with stakeholders. And that's going to be, a lot more efficient just so for our next cohorts, they'll be able to build on the foundations to make progress. We're optimistic that in the next year, we'll be able to continue with the proposed timeline, and we'll be able to, conduct these periodic semi-interviews, surveys, self-reflections, journals, and just be able to transcribe and analyze all of our data. Yeah, and that concludes the current updates of our Mother 3 HMT project. We thank all of you guys for your time, and now we'll open the Zoom for discussion, questions, or possible avenues for collaboration.
Yeah, thank you. I had a question about trust models. Usually we hear about human trust in an autonomous system, but I'm wondering about, earlier we heard about how autonomous systems can sometimes have better situational awareness than humans. Do you think that autonomous systems should carry a trust model of humans and not always trust their human teammates in the heterogeneous system? Humans are make a lot of mistakes, right? So
I've seen that a little bit, Kurt, on that robot that avoided kids at the mall by driving closer to the grown-ups.
I haven't seen that.
Yeah, Jessica.
You haven't seen that? Oh, that's a really funny. There's a good YouTube video on it. But yeah, the kids would harass robots, like I guess they're floor cleaning robots or something. If the kids, but the researchers determined through this work that if the kids were nearer to adults, they would stop harassing the robot. So the robot would drive closer to adults in order to avoid the kids harassing it. So it was, I thought, trust model based on height.
To add on to that, some of our students attended a conference recently for the Society of Experimental Test Pilots, and we asked them, informally about what they think of autonomous systems being able to control aircraft. And almost all of them that were in the room with us said something along the lines of, I want the final say. Even if this is a life or death situation, they still want that ultimate control over their aircraft. And so when we have autonomy that is going to take over human intervention, that's something that we need to keep in mind. And of course, it is going to be different based on populations, the difference between experimental test pilots versus children at malls.
Mm-hmm.
There was one presentation that we did view at the test pilot, and pretty much what it was on the physiological effects that happen during test piloting. So a lot of these physiological defects include like hypoxia, hypocapnia, hyperventilation, and they were trying to integrate this system that pretty much can predict or determine when these effects are going to happen. And essentially it creates a safer piloting environment and will allow for a system to alert ground control that pretty much something might be going wrong with the human that's the pilot. And then from there, ground control can try to communicate that to the pilot directly, just asking them, are you okay, what's going on there. And it's one of those things where as long as you're proactive in the solution, you'll allow for more pilot safety. And I think, like Jessica was saying earlier, one thing that they really stressed was, as a test pilot and as a pilot in general, most of these pilots, they want the last say, because at the end of the day, it's their life, and they want to make sure that they're in control of that final opportunity, I guess, to fix what's going on.
Sure. Yeah. I had another question. I think for you, Cesar. You had mentioned the IRB. Is that a CSUN IRB or is that the NASA IRB that you're going through?
I think Dr. Ho can elaborate more, but we have already submitted and have been reviewing the CSUN IRB. We've already received the first round of edits, and so a lot of it has to do with creating protocols for all of the data collection methods we intend to use, especially considering the ever-changing COVID restrictions.
Yeah, but Kurt, it's CSUN IRB, Kurt, and we got the letter from JPL, from Mitch Ingham, our point of contact, saying we can work with JPL, and I've been going after Nelson, and Nelson is in consultation with the Armstrong legal team to give us a go ahead that the CSUN IRB plus condition like we only do things that are approved by Armstrong, that reviewed by you before we publish any result and so on. That's something I'm working with Nelson, but I hope to get that done soon as well. Yeah. But Kurt, I want to go back to your earlier comment, and I think the student did a great job in answering your question. And I suspect the point you're making about to what extent should the machine trust the human? I suspect that will become an outcome of our work, because we start hearing that so much. And the Lee model that I think was Sean or Andy presented earlier only has this notion of humans, showing vulnerability, machines showing vulnerability to human, but maybe it's got to be this bidirectional trust as well, where now, the human needs to be vulnerable in some way for the machine to rely on it, and the machine vulnerable so the human can rely on them. And I think that's something that has not fully explored. And I think a lot of it is now we're asking the machine teammate, is it a lesser teammate? And if you talk to the test operational community, and those of you who know, when you walk in a room with the test community, don't tell me I said this, somebody told them you walk in a room full of eagles, right?
Yeah, well, no, that's true.
And I think Kurt and Nelson and Janu, you work in the test community, you know what I'm talking about. But I think, that may necessarily be true for the everyday average user, the drivers of Tesla, for example, right? You see things that way.
Or, well, I'm interested in sort of that middle ground where like air taxi pilots, right? So they're definitely not going to be trained to the level of a test pilot. They're probably not going to be trained to the level of a commercial airline pilot, but they'll have more training than, well, maybe than a driver of an automobile. But it's very likely that they may make poor decisions that need to be overridden. And so that I'm really interested in that human machine teaming problem, I guess.
Right.
And how do we solve that?
Right, and I think AutoGCAS already laid out some groundwork for that, right? With the notion of taking over when the human is incapacitated or disoriented and so on. But I think we're going to the next step, should like something like AutoGCAS takes over, like you said, like the average driver can't handle a certain situation. And I suspect that would be a direction of the work that we're doing, where we're gonna have to build a parallel model to the one that has been created before, and maybe use some of these cases to help substantiate what would be the antecedent of trust. How do you calibrate that trust? How do you repair the trust? What are other factors like autonomy level, reputation, cultural factors? I think a lot of things need to go in place, and that's really exciting for us looking into this work in year 2.
Ginu, you have your hand up?
Yeah, so that was excellent discussion. I just wanted to point out, even though the test pilots will say that autonomy, it's just human nature that after you use automation for a while, you implicitly develop some trust in it, and you even start to use it, in not the intended way. You kind of see it a lot with the autonomous driving and people taking a nap while the car drives. So it's a really interesting and excellent topic to explore further, especially in terms of airspace management, where you have FAA airspace controllers interacting with maybe autonomous machines that also has to share space with regular pilots. So yeah, really interesting discussion.
Okay, so we're pretty close to the end. I was going to introduce Mitch, but I think he just left. Mitch is no longer in the room. Mitch Ingham is our one of the most important figures we have that helps us collaborate with JPL, but I was going to give him a chance to say hello for at least a minute. But Newt, do you want to close it out? And I just want to thank everybody for showing up, everybody for going through this whole 4 hours with, or 4 hours with us. And the students, wonderful work, wonderful presentations throughout the day. But Newt, you have the final word. Or
Yeah.
anybody at NASA, if there's anything you want to say.
Yeah, I agree with you. You know, really great thank yous to all of our students and congratulations to all of our students. I think you all are doing really phenomenal work and really important work. And also thank yous to our wonderful faculty members who, you know, carry on and help the student and being the bridge to the NASA collaborators. And also thank you to all the NASA and JPL collaborators who kind of showed up at different times of the day today. And lastly, you know, to our TRC, you know, you survived us, right? We have a few more video and we have more video and presentation, but Joe and I said, you know, let's just do this. I think this is kind of long enough, but I think next year we need to do this in person so we can do us justice, so that we can invite more folks. And Kurt, so you can visit us for the first time.
Yeah. Yeah, I want to say thank you so much to the faculty and especially the students. These were all great presentations. It's great work. It was fun listening to what you all are working on, and I look forward to seeing how it progresses over the next couple of years. So.
And by the way, Kurt, we start having a lot of publications. Sarah and I are working to pulling the list together, and we either include that in a report or share that with you. Just like, I don't know, you attended the AIAA Ascent conference this week. We had three presentation in the HMT sessions. Yeah, Thomas, Lilo, and I think Neil paper was there. So yeah, we started getting publications out. So it's all good.
Okay. I think I need to put together a some sort of write-up for the Miro folks about this meeting. So actually, if you could make the slides available, that would help jog my memory on all the things I heard today. I took notes, but it would be nice to have the slides as well. So, and then if there's additional presentations, I'd like to be able to view those. So,
absolutely, Gino, you go ahead.
Gino, yeah.
Oh, sorry. I think I just forgot to lower my hand. Okay, let me try to find this button. Okay, yeah, sorry about that.
No worries.
I'm surprised there's not a little pop-up that says, "Hey, you've had your hand up even though you finished talking." Like, you sure you want to do that?
Need some.
It's like a good thing for a robot to do.
All right. Anybody else? Last thoughts, last words. So I'll prep that series of presentations and a couple of those video links for you as soon as we can. But again, thank you everyone. Appreciate all the faculty, NASA, and then all the collaborators that showed up too during this 4-hour session, and then of course the ARCS staff and students that have been involved on putting this together. So thank you everyone for doing this. We recorded it all too, by the way, Kurt. So I can give you a link to that if you want to scrub through it. But thank you everyone again, and I'll close out the meeting. All right, bye everyone.
Thank you. Bye.
Everyone take care. We also have this recording, right, Joe? So we'll be able to disseminate.
I have the whole thing, yeah.
Let's use the last one standing.
Joe, I was thinking maybe it wouldn't be a bad idea